Yes, thank you very much, Julia, for your kind introduction, and I'm very happy to see you today for my talk. As just announced, I will tell you a little bit more about reformer technology that we are developing at Fraunhofer IMM. But before going too much into detail, I would like just to start with a very brief introduction. And I think you all know that despite Germany is reducing its CO2 emissions, still the current reduction is not enough to reach the 1.5 degree Paris aim. So, which means that the increase in temperature is expected to be even higher, and of course it will lead then to such pictures that we saw also during last years very often in all the newspapers. But despite from this ecological impact, what we also of course have to keep in mind, and I think we are all aware of, is the CO2 price. So we expect that this price will increase even further and further during the next years, and it basically means for us that of course we need to reduce CO2 emissions, and basically the energy transition is the key. And therefore, hydrogen was identified as a key compound for the current energy transition, because basically the production of hydrogen causes no CO2 emissions. It can be produced from renewable energy sources. But there are certain drawbacks which I would like to mention very quickly. So first of all, it has quite a low volumetric density, and the transport of hydrogen is quite difficult. So the energy demand for liquefying of hydrogen or for compression of it is quite high. So it's clear that, for instance, hydrogen will not be produced in Germany. It rather will be produced in other countries where a lot of renewable energy is accessible, and therefore such hydrogen derivatives like methanol and ammonia started to play a more important role, because they are basically easier to transport, and there is already existing infrastructure for these chemicals, so which means that we can produce it in another country like Australia or Chile, and then transport it via the existing infrastructure to Germany. But of course, when we have now methanol or ammonia, we need to get hydrogen back, and therefore it requires a certain technology at the application side. Just like a quick reminder, so here on the slide you see the chemical reactions on the left-hand side. That's splitting reaction for ammonia cracking, on the right-hand side methanol reforming. So both reactions are equilibrium reactions, and both of them are endothermic, which basically means that it requires heat to run the reaction. And therefore, the sufficient heat transfer is basically the key to keep the system efficient. And exactly here, it's where Fraunhofer IMM comes into this game, and I would like to briefly introduce you our reactor strategy. So we are IMM, Institute for Microsystems and Microengineering, and our reactor design is based on such microstructural plates, as shown here on the left-hand side. Then we coat these microstructural plates with the catalyst, which we develop ourselves at the institute, and then at the end these plates are assembled to such a reactor as shown on the right-hand side. And the unique thing about this strategy is then the plates, which are then coated with the catalyst, are combined in a way that in one layer we have this endothermic reaction, and in the second layer below, so as shown here, we can have, for instance, combustion of the off-gas from the purification step, and get the heat very, very efficiently to the catalyst. Therefore, we have a very high efficiency, and this efficiency, on the other hand, allows us to get a very compact system and to reach about 90% size reduction in comparison to a conventional system. We are using catalyst coating, as I told you before, and it's actually also, it has a certain advantages in comparison, let's say, to fixed bed or other conventional technologies, because we are minimizing the effect of mass transport limitations, and it allows us to reach one order of magnitude higher activity in comparison to conventional technologies. And also the catalyst we developed in the institute showed proven stability and activity. So at the institute we are able to develop the entire systems, not only the reactor, but for instance in the case of methanol you also need to purify, of course, your steam, because it has also CO or CO2, and for instance for fuel cell applications you want to get rid of it. So we are able to provide you with the fully automated systems, including hydrogen cleanup, and also the technology is quite scalable. Here is just as an example for methanol reformer from 6 to 100 kV, but actually currently we are also working at larger systems. For instance, for methanol, currently it's 300 kV, but I will tell you about it later. Regarding ammonia cracking, here you see the existing system at our institute. It's a demonstrator plant for the ammonia feed up to 21 kilo per hour. So actually quite a good ammonia or quite a large ammonia feed. It corresponds to 50 kV electric power equivalent. And as you can see here, so the total size of the system is about 180, but it also includes the entire periphery like evaporator, superheater, and so on. So the system is quite compact. And here is a real picture of the ammonia cracker with this integrated combustion heating, as I explained you at the beginning of my talk. We tested, of course, the demonstrator performance. It's quickly shown here. So we investigated it in the temperature region 600 to 650, also at the different ammonia feed flows, here shown on the right-hand side, up to 18 kilo per hour. And under all investigated conditions, we were able to reach more than 99.5% conversion. So next steps and some outlook. Currently, we are also working at the operation of such a demonstrator at higher pressure because it's very relevant for further purification steps. So we want to combine the system, for instance, with a pressure swing adsorption to get then hydrogen in a purity which is required for such a fuel cell. We are also involved in a European project Gamma, where the idea is to use such compact and efficient reformers for the electricity generation on a ship. So we will provide a container-based solution of our reformers. So to generate 1 megawatt power, 600 kV will come from methanol reformer and 400 kV from ammonia crackers. Combined then with the purification step and fuel cell on the board. And last but not least, what I would like to mention is a combination with a combustion engine. So here we work together with American company First Ammonia Motors. They retrofitted an existing combustion engine and combine it with our ammonia cracker, because probably you know that ammonia is not burning very well on its own. So by utilizing of our crackers, we're then able to generate hydrogen ammonia mixture, which is then combusted much better. And this pickup is already on the road of North Carolina. If you would like to see a video, then please pass by at our booth, E10, in this hall. And I'm at the end of my talk and happy to take your questions, if there are any. Thank you for your attention.